Hey everyone, I'm going to do chapter 16, problem number 15. Uh, this one, the problem gives us current in time form, and it wants us to convert each one of those into phasor form, and then it wants us to find the phasor form for the total current, and then the uh, total current time domain. So the thing to remember about RLC circuits is that each one of these has a particular uh, angle on a chart here, where this line here is your resistors, these are your capacitors, and these are your inductors. So for each one of these, the magnitude would go along this. Like first, for example, for your resistors, magnitude here is 7. For your inductor, your magnitude is 4, so it's a little bit shorter. And then for, for your inductor, it's 4, so it's shorter than the 7. And then for your capacitor, it's 6. It goes up almost as long as the 7. So from here we know that from my physics class, basically what we did was we would plot these out in this form. And what this tells you is, okay, the 6 is greater than the 4. That cancels out. This winds up becoming 2, right? Because 6 from 4 is equal to 2. This 7 is going to pull on that 2 harder. So you're going to wind up with something that looks like that. It's going to have some angle above the resistance line. So, being that as it is, that hopefully that explains what's going on. But to get this from your time domain formula to phasor form, what we need to do is remember that phasor form, it's going to be I effective multiplied by the angle, whatever it is. I'll put the theta here. I'm sorry. It looks like, let's rewrite that. It looks really bad. So it's going to be I effective, and then the angle at which it's dominant here, I, R, or C, whatever it is. So I effective is basically your maximum. So for this example, 7 multiplied by 0.707, which is 1 over the square root of 2. I'll write that here, 0.707. Okay, so for this first one, we have 7 sine of omega t. Now remember, this first one is a resistor, so there is no angle because it's horizontal to the plane. So 7, let me turn this on, sorry. 7 times 0.707, we wind up with 4.94. And just to explain what's going on here, do 7 divided by the square root of 2, and we'll get the same answer, essentially. So we'll call that 4.95. So let me change my color. 4.95, and the angle here is 0. The next one, 4 times sine omega t minus 90. Remember, because the inductors, they pull downward. So let me change my color and go back to here. We have 4 times 0.707, 2.82. We'll call that 2.83. So 2.83. This angle is minus 90. minus 90. The last one, 6 sine omega t plus 90. 6 times 0.707, 4.24. Change my color back to orange. 4.24, and that angle is at 90 degrees. So these here are the phasor forms of each one of these amperages. So the total would be the sum of all of those. So IT is going to equal 4.95 plus 2.83 at angle negative 90 plus 4.24 at angle 90. Now, if you don't know how to add these up, you might want to watch the previous video I did. But essentially what we need to do is convert these into complex numbers. And we know that cosine of 90 is 0, so there won't be any real numbers for each of these. And this is pretty self-explanatory because they only go in one direction. They're not, they either go straight up or straight down. They don't go across. So it's either a negative I or a positive I. So what we wind up here is 2.83 times the sine of negative 90, which is 2.83 negative, right? Because sine of 90 is 1. 2.83 I negative because it's a negative 90, and then this one's going to be exactly the same thing. It's 4.24 I, but in the positive direction. This 4.95 is just 4.95 because it goes straight across. So when we add all those up, and we can do that here in this calculator, 4.95 plus a negative 2.83 2.83 I plus 4.24 I, we get 5.15 at angle 16 degrees essentially. So 5.15 at an angle of 16 degrees. That is your phasor form for IT. They call that capital IT when it's in phasor form. Now you want to find time domain. When we went from time domain to phasor form, we multiplied by 1 over the square root of 2. So to find this magnitude, we would multiply by the square root of 2. So we get 5.15 times the square root of 2. We wind up with 7.28. 7.28. And sine omega t plus 16. Now let's go back to what we had talked about at the beginning. We said that it wouldn't be less than 0 degrees, so we know that. And we said that this horizontal 7 would pull on this 6, or actually the equivalent of 2 after you remove the inductor pull, and it would be just kind of above the resistance axis, and that's what we show here. It's only 16 degrees above that axis because the 7 is pulling harder than the 2. So I hope that helps you guys out. If you have any particular questions, please let me know.